Chapter 3. Gas Exchange Processes. Scavenging. In an internal combustion engine, this is the removal of exhaust gas from the cylinder after combustion and its replenishment with air for subsequent combustion. Efficient scavenging is necessary for good combustion, and it is required for the very first working cycle of the engine. The passage of scavenge air will also assist cooling of the cylinder, piston and valves. Scavenge of four-stroke engines. Scavenging in four-stroke engines is carried out mainly by the pumping action of the piston during two of its strokes. The piston expels exhaust gas on its upward stroke and draws in air on the subsequent downstroke. The scavenge diagram, figure 27, which is on page 25 of the book, shows that there is a period of overlap during which exhaust and inlet valves are both open together. Provided the turbocharger supplies air at a pressure greater than that in the exhaust manifold, a flow of cooling air will pass through the cylinder during this period. Scavenge is positive and very efficient, even in the very high-speed four-stroke engines. Scavenge of two-stroke engines. Two strokes rely on a charge of scavenge air under pressure sweeping through the cylinder and expelling the exhaust gas in front of it. This process must take place while both scavenge and exhaust connections are open and the piston is near the bottom of the cylinder. Even in slow-running engines, this allows only a very short period of time for scavenge to be completed. Some mixing of air and gas will occur, but this must be kept to a minimum, and scavenging can be improved by supplying a volume of air in excess of the cylinder volume, the excess passing to the exhaust system. Scavenge air in a two-stroke engine must be supplied to the cylinder at a higher pressure than that in the exhaust manifold. In modern engines, this is provided from exhaust gas-driven turbochargers, the air being cooled to increase its density and cooling capacity. Earlier engine models used a variety of methods to supply scavenge air, such as pumps, rotary blowers, and compression from the underside of the piston on its downward stroke. All these added to maintenance work, absorbed part of the power produced by the engine, and were only able to supply limited quantities of excess air. In large, slow-running engines, the air enters the cylinders through a circumferential row of scavenge ports cut in the liner and uncovered by the piston as it moves towards the bottom of its stroke. They are closed at a symmetrical timing on the following upstroke. The exhaust valve must open before ports are uncovered to allow a period of blowdown. Blowdown is the release of gas pressure at the end of expansion as the exhaust valve opens. Gas passes to the manifold, carrying its remaining energy to the turbocharger. Cylinder pressure drops rapidly to a value below that in the scavenge trunk, allowing air to enter. There are three basic methods of scavenging within the cylinder. They're shown in figure 28, which is on page 27 of the book. Method A is loop scavenge, in which air passes over the piston crown and rises to form a loop within the cylinder, expelling gas through exhaust ports cut in the same side of the liner above the scavenge ports. B is cross scavenge, where air is directed upwards, passing under the cylinder over and down the opposite side, expelling gas through exhaust ports on that side. C is uniflow or through scavenge, in which air passes straight up through the length of the cylinder, forcing the exhaust through ports or valves at the top of the cylinder. In all these, the swirl or direction of the air is assisted by the port edges being angled in one or two planes and by the shape of the piston crown. In cases A and B, a piston skirt or exhaust timing valve will be necessary to prevent scavenge air leaking to exhaust while the piston is at the top of its stroke. Case C tends to give the highest scavenge efficiency with the least mixing of air and gas. It may also be used with greater stroke-bore ratio and in opposed piston engines. It avoids the difficulty of high temperature gradient between adjacent scavenge and exhaust ports in A, or the temperature difference on opposite sides of piston and rings in B. Uniflow or through scavenge with a large centrally positioned exhaust valve is used in most modern slow-speed large engines. It allows design of efficient long-stroke engines and is less susceptible to damage from the products of combustion from low-quality heavy fuels. Absence of exhaust ports allows the liner to be of simpler construction. Piston skirts are not necessary, and cylinder lubrication is satisfactory and economical. The scavenge air trunk forms part of the engine structure and must be of sufficient size and shape to supply even quantities of air at constant pressure to all cylinders. It must be maintained in a clean condition and be regularly inspected. Pressure relief valves are fitted for safety. Pressure charging. Here, the charge of air in the cylinder before compression commences is above atmospheric pressure. Pressure charging, sometimes called supercharging, forces a greater mass of air into the cylinder for combustion, and consequently a greater quantity of fuel can be burned efficiently. Power output is increased, giving a higher thermal efficiency with no increase in size. Pressure-charged engines must be designed to operate safely under the high loads and temperatures which may be caused. In most modern engines, high air pressures are supplied by means of exhaust gas-driven turbochargers, and consequently the general term turbocharged engine is used for both 2- and 4-stroke engines. Turbocharged systems. Most modern engines are turbocharged to increase the power output and efficiency with only a relatively moderate increase in size, weight, and initial cost. The efficiency of the system is increased by fitting a charge air cooler after the compressor. This is shown in figure 29, which is on page 28 of the book. This will cool the air at constant pressure, increasing its density before supplying it for compression in the engine cylinders. The mass of air per cycle can now be increased, and the quantity of fuel injected can be raised to give a corresponding increase in engine output and thermal efficiency. Exhaust gas from the cylinder operates the gas turbine, giving up some of its heat energy to do so. The turbine drives a directly coupled air compressor, which draws air from the atmosphere, compresses it, and then cools it in the charge air cooler before supplying it to the engine through scavenge ports. The turbocharger is free-running, and at any engine speed the exhaust gas energy must cause the turbine to run at a stable speed at which the compressor will supply the correct mass of air to the engine. It is then said to be matched to that engine, and it must remain matched over the full main operating power range. When an engine has 2 or more turbochargers operating in parallel, they must all be matched. Matched systems may become unstable and surge if fouling or damage occurs. A turbocharged system may be designed to operate on either the pulse or the constant pressure exhaust system. Pulse system. The main energy to power the turbine in this system is derived from the pulse or impulse energy in the pressure waves formed during blowdown from each cylinder. These waves travel through the manifold to the turbine nozzles, where they are converted to kinetic energy at high velocity to rotate the turbine blades. This system gives a rapid build-up of turbine speed when an engine is started or manoeuvring. To maintain the pulses, exhaust connections are of limited diameter. No sharp bends are used, and the turbocharger is fitted close to the engine. The peak pressure in pulse waves may be higher than the pressure in other cylinders whose exhaust valves are open, and to prevent a backflow into these it is necessary for multi-cylinder engines to subdivide the exhaust between a number of manifolds, each with a separate nozzle box at the turbine. Up to 3 cylinders can use each manifold without interference according to their firing order. A divided exhaust system replaces turbine efficiency and may require more than 1 turbocharger per engine. The use of pulse converters in modern engines allows individual cylinders to exhaust to a common manifold, giving higher turbine efficiency and a more compact system, which allows rapid acceleration when manoeuvring. Constant pressure system. Here, all cylinders exhaust into a common receiver, large enough to change pulses to a steady pressure. This system has one connection to the turbine which, due to the common nozzle ring and steady pressure conditions, can be designed to operate at a higher thermal efficiency. High-efficiency turbochargers can operate effectively down to about 25% of full engine power. This system is slower in its build-up of pressure when starting, and insufficient air is available for 2-stroke engines during manoeuvring or operating at low speed and low power. To overcome this difficulty, modern engines have electrically driven centrifugal compressors fitted to augment the air pressure in the scavenge trunk when necessary. These are driven by constant speed, low power motors controlled to start automatically if scavenge pressure drops. They draw additional air through the main turbocharger air intake and charge air cooler, discharging it through non-return valves to the scavenge box for the cylinders. Turbochargers. Figure 30, shown on page 29, shows a section of a turbocharger as fitted to large bore engines. It consists of a single-stage axial flow exhaust gas-driven turbine mounted on a common shaft with a centrifugal air compressor. The turbine has a nozzle ring followed by a rotating disc with a single row of moving turbine blades. These blades are attached to the disc by fir tree-shaped roots, and they have free room to expand when heated. Binding wires are fitted to the blades to reduce vibrations. Blades and nozzles are manufactured of heat-resisting steel or nickel alloy. The turbine casing is in two parts, both of cast iron, with adequate water cooling spaces. There are inspection and cleaning covers to these spaces which are circulated with fresh water from the engine cooling system. A drain valve is fitted in the exhaust gas space. The air compressor consists of a radial flow impeller disc together with an inducer. Both are of aluminium alloy. The impeller discharges air through a diffuser to a volute casing. Compressor casing, also in two parts, is of cast aluminium and is uncooled. Air is drawn from the engine room atmosphere through inlet filters which may be removed for cleaning. Air inlets are streamlined and fitted with insulation internally to reduce noise. The turbine nozzle ring, air diffuser, impeller and inducer will be replaceable to allow matching between turbine and compressor and between turbocharger and engine. Two labyrinth seals are fitted to the shaft, one between the thrust bearing and air compressor and the other between the turbine and the bearing. They are sealed with air under pressure from the compressor discharge through internal passages and restriction plugs. Air from glands passes to the atmosphere or assists cooling of the turbine disc. The seals prevent possible oil leakage into the turbine or compressor, or exhaust gas into the corresponding bearing oil. Some air will pass down the back of the impeller through a labyrinth arrangement, along the turbine shaft, assisting cooling, and leaving with the turbine exhaust gases. Two shaft bearings are fitted, one at each end, allowing accessibility and cooling. End thrust is taken at the compressor bearing, the turbine bearing allowing expansion adjustment. Bearings may be either a plain sleeve type with copper lead bushes on hardened steel shaft sleeves, or, alternatively, ball and roller types. These reduce friction drag, but are susceptible to vibration and fatigue, both when running and also from externally generated vibration when not in use. They must be fitted in resilient mountings which use springs and oil damping in both axial and radial directions. These bearings have a fixed fatigue life and they must be renewed at stated intervals, say 8,000 hours. Lubrication of the bearings may be by various means. Ball and roller bearings may be lubricated by self-contained gear-type pumps operated from the shaft and drawing oil directly from the independent bearing sump. Oil level must be maintained in these sumps, and the oil should be renewed at stated intervals. Alternatively, the bearings may be lubricated by external systems, either by connections from the engine lubricating system through a fine filter, or by an independent system of pumps, coolers, filters, oil sump, and alarms. Independent systems allow a choice of turbine oils to be used. All lubrication systems must maintain adequate lubrication when tilted to an angle of 15 degrees in any direction, or a temporary tilt of 22.5 degrees. Updraft in the exhaust system may cause the turbocharger to rotate while the engine is out of service, so care must be taken to ensure no damage is caused to bearings from lack of lubrication or by vibration transmitted from other systems while the engine is stationary. Sleeve-type bearings are less susceptible to this damage. With large turbochargers fitted with sleeve bearings lubricated from the main engine system, a gravity tank must be fitted to ensure adequate lubrication in the event of pump failure or stopping of engine-driven pumps. Some models of turbochargers are designed with both rotor shaft bearings situated on the centre section, allowing the turbine and compressor to overhang at each end. This may reduce the overall size and weight and economise in the shape of air inlet and exhaust connections, but it will require larger bearings and the oil to them must be cooled. Central bearings are less accessible for maintenance. Uncooled turbochargers. Uncooled turbochargers do not have their turbine casing water cooled. In general construction they are similar to those already described, but some changes are necessary to accommodate the higher gas temperatures. The casing is manufactured from cast steel and insulated to conserve heat and meet safety requirements for hot, exposed surfaces. Figure 31, on page 31 of the book, shows a cross-section of a brown Bovary BBC VTR4 uncooled turbocharger as fitted to many large two-stroke engines. The turbine bearing will require cooling. In this case, it is protected by insulation and also has a water-cooled casing which maintains acceptable oil temperatures. Higher working temperatures will eliminate the possibility of condensation and acid corrosion within the gas casing. The final outlet gas temperature may be up to 10 degrees centigrade higher than that from cooled turbines, and this is attractive for large, slow, two-stroke engines which produce limited exhaust temperatures. This allows more efficient use of a waste heat boiler, and therefore adds to the total heat recovery and thermal efficiency of the plant. Cleaning of turbochargers. Under operating conditions, turbocharged systems may become fouled, giving reduced efficiency, loss in power, and maybe surging. Compressor surfaces can be contaminated by oil and dust drawn from the engine room atmosphere, passing through the intake filters and adhering to working surfaces. This gives loss in compressor efficiency and chokes the charge air cooler. Contamination can be removed while the engine is running by water washing. A small spray of clean, fresh water is injected into the airstream at the compressor inlet. Water droplets are drawn through and scour the surfaces clean. Water drains must be open, and the quantity of water limited, since some of this, together with contaminants, may pass into the engine cylinder. Additives to improve the cleaning effects of the water must not be used in trunk piston engines, where it is possible for them to pass through the cylinder and into the crankcase oil. Hydrocarbon-based additives must not be used, since there may be an explosion risk, and they may also add further combustibles to the cylinder which have bypassed the governor control. Fouling of the exhaust system and turbine is the build-up of the products from combustion of fuel, used cylinder oil and its additives, ash, and any other non-combustibles present in the fuel. These will create hard deposits which interfere with gas flow, may cause local overheating, reduce turbine efficiency, and even destroy balance of the rotor. Water washing may also be used to clean the gas side of the system. A small water jet sprayed into the gas stream before any grids in the turbine will dampen and soften the deposits, reducing adhesion and enabling them to be blown clear by the gas stream. The introduction of water to very hot surfaces can cause thermal shock, so before water washing, the turbine engine power must be reduced so that temperatures in the system are lowered. Water drains must be open and great care exercised, since removal of deposits may affect the balance of the turbine rotor. Examination and more comprehensive cleaning of parts by physical and chemical means can be carried out during overhaul. Charge air cooler. In modern two-stroke turbocharged engines, a charge air cooler is necessary. Compression will raise the air temperature, and a charge air cooler is fitted to reduce the temperature of the air between the turbocharger and the engine inlet manifold, causing increased air density at lower induction temperature. The engine is maintained at safe working temperatures, and the lower compression temperature reduces stress on piston rings, piston and liner. Increased density will raise scavenge efficiency and allow a greater mass of air to be compressed. More fuel may now be burned, giving an increase in power. Figure 32, on page 33 of the book, shows a section of a charge air cooler. The air makes a single pass through the cooler, and for efficient cooling its velocity should be low and cooling area large. This is obtained by making the air inlet connection divergent. The outlet is convergent to restore air velocity after cooling. Condensation of moisture in the compressed air will occur during cooling, and a drain is fitted to the outlet side air casing to allow this condensate to be removed. A moisture eliminator may also be fitted to remove entrained water droplets from the air stream. The drain should be kept open and its discharge noted. This will also indicate if a cooling water leak has occurred. The cooler consists of a tube stack of aluminium brass tubes rolled and solder bonded into two brass tube plates. Cast iron water boxes are attached to tube plates and allow saltwater circulation within the tubes to make two passes. One tube plate is secured to the casing while the other is free to move axially as thermal expansion occurs. The air seal is maintained by means of a fitted rubber joint ring. An air vent is fitted to the top water box to remove air which may have been released from the saltwater system. Corrosion plugs may be fitted within the water space. Thin copper fins are soldered to the outside of the cooler tubes. The air will pass between these plates, which greatly increases the area of heat transfer. There are two side plates of mild steel or aluminium alloy. Temperatures and pressures are recorded at each inlet and discharge. Discharge air temperature should not exceed 55 degrees centigrade, since engine temperatures, notably the exhaust temperatures, will increase, with loss in efficiency due to reduction in air density. Air at very low temperatures will also cause thermal shock when in contact with hot liners and pistons. Undercooling of air occurs when it is cooled to a temperature below the dew point at that pressure. To prevent undercooling and excessive condensation, air temperature should not be taken below 20 to 25 degrees centigrade. Some measure of cooler efficiency can be ascertained from the difference between air discharge temperature and cooling water inlet temperature under normal running conditions. A rise in this indicates fouling of the cooler. An increase in the air pressure drop indicates fouling of the air passages, while an increase in water pressure drop indicates fouling of the water side. When necessary, charge air coolers can be cleaned while out of service. Waterside may be cleaned by removing water boxes and brushing through tubes. If this does not remove the scale, acid cleaning may be carried out, after which it must be flushed through. After cleaning, a pressure test should be carried out on the water spaces. Air passages may be blown clear with a compressed air or steam jet, and specially shaped brushes may be used. If these do not remove the dirt, the stack may be immersed in a hot degreasing fluid and then blown clear. Exhaust valves. One or more exhaust valves are fitted to each cylinder within the cylinder cover and are of the poppet type, with their valve lid and spindle of inverted mushroom shape arranged to open inwards in order to maintain positive closing under pressure in the cylinder and ensure their non-return action. Gas pressure will act upon the area of the valve lid to hold it against the seat and supplement the closing action of the springs. This positive contact of valve and seat removes carbon or other deposits on the valve seat which, if allowed to build up, cause blow-by of hot gases and burning of valves and seats. The shape of the valve lid protects the seat from the flame and hot gases during combustion. Four-stroke engines, together with some older two-strokes, have their exhaust valves mechanically actuated from a camshaft, the shape of the cam controlling the timing and the lift of the valve. Rotation of the cam peak raises a follower and pushrod to operate a pivoted rocker lever, the other end of which depresses the valve spindle through a tappet and causes the valve to open. During opening, the valve springs are compressed, and these force the valve to close as the cam peak leaves the follower. Helical valve springs are used, designed to have sufficient compressive strength while avoiding vibrations. Valve springs and operating mechanism can be of moderate proportions, reducing inertia of parts and power demand. To facilitate overhaul of the valves without removing the cylinder cover, valves, together with their springs and so on, may each be fitted in a separate cage. Exhaust valves may be manufactured from heat-resistant alloy steels, but to prevent corrosion when burning heavy fuels, stellite surfaces are added at valve landing surface and in way of the guide brush. Alternatively, the whole valve may be made from pneumonic high-nickel alloy. Cooling of exhaust valves will prolong the useful life of valves, seats and bushes. It will maintain temperatures low enough to prevent burning and rapid wear, and also allow lubrication of the spindle bushes, reducing wear and maintaining valve alignment. When burning heavy fuels containing vanadium and sodium compounds, valve temperatures must be kept below 530 degrees centigrade, above which deposits and corrosion may occur. Cooling is by circulating the valve cage and seat with fresh water. In some cases, the valve itself may be cooled by cooling passages with flexible external connections. Valves and seats should be made of materials which readily conduct heat from the valve lid. Valve cages must be a good fit in the cylinder cover in order to transfer heat to the cover. Rotation of valves during operation will assist in removal of deposits between seat and landing. It will also ensure even temperature and wear around the valve. Rotation may be carried out mechanically by fitting a ratchet or friction device at the top spring compression plate, or pneumatically by fitting angled guide vanes to the valve spindle. These cause the gas stream passing through the valve to rotate it while open. Tappet clearances are necessary to allow for thermal expansion of the valve spindle length at working temperature, and to ensure that positive closing of the valve continues as it wears or seats during use. Clearances should normally be set while the engine is cold and the cam follower is off the cam peak. Wear of the valve gear will tend to increase clearances. Excessive tappet clearance will cause the valve to open late and close early in the cycle, and will reduce its maximum lift. It will also cause noise and eventually damage from the impact of working surfaces. Insufficient clearance will cause the valve to open early and close late, with increased maximum lift. In extreme cases, it may prevent the valve from closing completely as it expands or beds in. This, in turn, will cause hot gases to blow past valve faces, causing valve burning, low compression, and so on. Hydraulically operated exhaust valves. This type of valve is now fitted to most large two-stroke engines. The pushrod, rocker lever and tappet are all replaced by a hydraulic system. The exhaust cam follower raises the piston of a single-acting high-pressure oil actuating pump. As the piston is raised, it delivers oil at high pressure through a reinforced pipe to a hydraulic piston attached to the top of the valve spindle, forcing the valve to open. When the cam peak has passed, a helical return spring forces the follower down onto the cam profile, lowering the actuating position and releasing the hydraulic oil pressure. This allows the valve spring to force the valve closed, returning oil from its hydraulic cylinder. Each hydraulic valve system is continuously charged with oil from the main engine lubrication so that any leakage is immediately made up. Some early valves of this type had helical valve springs, but present practice is to use an air spring or pneumatic piston in which air under pressure is further compressed as the valve opens. This pressure energy is stored in the air spring and used to close the valve. Air springs are charged continuously from the main air start supply through a reducing pressure valve. This ensures the appropriate exhaust valves are closed before the engine can be started. This system has many advantages over pushrods. It reduces overall weight, allows the designer to place the camshaft in the most effective position, reduces the power absorbed and inertia losses, eliminates side thrust on the valve spindle and spring surge or vibration. It also allows the valves to be rotated by the gas stream as described earlier. Air inlet valves are necessary in four-stroke engines and similar in construction and operation to the pushrod type of exhaust valve. They are cooled by the passage of cool inlet air and do not require additional water cooling or to be made of such exotic materials. Chapter 4. Engine Parts.